Hey everyone, welcome back to the AWS ECS video series. In our previous videos, we built a strong foundation by understanding the core concepts of ECS and seeing it in action. Now, it's time to level up. We're moving beyond the basics and stepping into the advanced world of ECS, where things get real, and where the focus shifts to running production-ready, highly available, and scalable applications. Let's quickly recap our ECS journey so far. We started with the basics of Amazon ECS, understanding what it is, and why it's such a powerful tool for running containers. Then, we deployed an Nginx container, first on EC2, and then on Fargate, giving us hands-on experience with both launch types. Next, we explored Amazon ECR, AWS's managed container registry, and saw how it helps us store and manage Docker images. And finally, we brought everything together by taking a Dockerized Node.js application, pushing it into ECR, and deploying it straight into ECS. In this video, we're going to dive into load balancing, one of the most critical topics when it comes to running production workloads on ECS. First, we'll start with the basics, what load balancing actually is, and how it helps distribute traffic efficiently across your applications. Next, we'll see why load balancing is critical for ECS, especially when you want your services to be highly available and scalable. Then, we'll explore the different types of load balancers AWS offers, and understand their unique use cases. After that, we'll focus on the application load balancer, or ALB, and why it is generally the best choice when working with ECS. We'll break down the ALB into its key components, so you know exactly how it handles traffic behind the scenes. Next, we'll take a look at the overall traffic flow, from the user request to your ECS tasks, and see how ALB manages it efficiently. Then, we'll introduce routing on ECS using ALB, including how requests are directed to the right containers. And finally, we'll touch on some advanced ALB features that can help optimize performance, security, and scalability for your ECS applications. Let's make load balancing easier to understand with a real-world example. Imagine a busy restaurant with multiple chefs in the kitchen. Customers come in and place their orders at the counter. Now, instead of giving all the orders to a single chef, which would slow things down and create chaos, the restaurant manager distributes the orders evenly to all available chefs. Each chef handles their share of the orders, cooks them efficiently, and the customers get their meals faster. This is essentially how load balancing works in the cloud. Just like the restaurant manager ensures no chef is overloaded, a load balancer ensures that no single server or container in your ECS service gets overwhelmed with traffic. This ensures orders are delivered quickly, the kitchen runs efficiently, and every customer leaves satisfied, just like a perfectly coordinated restaurant. So, what exactly is load balancing? In simple terms, load balancing is the process of distributing incoming requests evenly across multiple servers or containers. Instead of sending all the traffic to just one server, which could easily get overloaded, a load balancer makes sure the workload is spread out. This prevents bottlenecks, improves overall application performance, and ensures your services stay reliable even when traffic spikes. In other words, load balancing is what makes applications not only highly available, but also scalable, by allowing you to add or remove servers as needed, without interrupting the user experience. Now, let's talk about why ECS actually needs a load balancer. First, it gives your clients a single entry point. Instead of exposing every container or task directly, all traffic comes through the load balancer. This simplifies access and improves security. Second, it distributes traffic across your ECS tasks. Whether you're running 2 tasks or 200, the load balancer makes sure requests are shared evenly. Third, it handles failures automatically. If one task crashes or becomes unhealthy, the load balancer simply routes traffic to the healthy ones, without your users even noticing. And finally, it enables scaling. As you add or remove tasks, the load balancer adjusts automatically, ensuring your service can grow or shrink smoothly with demand. Now let's take a look at the different types of load balancers AWS offers. The first is the Application Load Balancer, or ALB. This one operates at the application layer, which means it's perfect for handling HTTP and HTTPS traffic. It also supports advanced routing, making it a great fit for most ECS workloads. Next, we have the Network Load Balancer, or NLB. This one works at the transport layer, giving you extremely high performance and ultra-low latency. It's ideal for workloads that need to handle millions of requests per second, or when you're dealing with TCP or UDP traffic. And finally, there's the Gateway Load Balancer. This is designed to deploy, scale, and manage third-party virtual appliances, things like firewalls, intrusion detection, or deep packet inspection systems. Each of these has a specific use case, but for ECS, the Application Load Balancer is usually the best choice. So, why is the Application Load Balancer the best choice for ECS? First, it has native support for HTTP and HTTPS, which makes it ideal for most web applications running on ECS. Second, it supports host-based and path-based routing. That means you can route traffic not just to one service, but to multiple services, based on domain names or URL paths. Third, ALB uses dynamic target groups, and for Fargate this works perfectly with IP-based targets. This allows ECS tasks to be registered and deregistered automatically as they scale up or down. And that brings us to the next point, automatic task registration and deregistration. ALB integrates deeply with ECS, so whenever a task becomes unhealthy, or new ones are launched, the load balancer updates itself with no manual intervention. Finally, ALB works seamlessly with ECS health checks and service discovery, giving you smooth scaling and rock-solid reliability out of the box. That's why, in most ECS architectures, the Application Load Balancer is the go-to option. Now let's break down the key components of an Application Load Balancer. First, the listener. Think of the listener as the doorman of the load balancer. It listens on specific ports, usually port 80 for HTTP and port 443 for HTTPS. Any request coming in from clients hits the listener first. Second, listener rules. Once a request comes in, the listener uses rules to decide where it should go. For example, imagine you're running an online store. Requests to /checkout can be routed to your payment service, while /products goes to the product catalog, and /cart goes to the shopping cart service, all running in ECS, behind the same load balancer. This is what makes ALB great for routing. Third, target groups. A target group is simply a collection of ECS tasks or IP addresses that will receive traffic. Each service in ECS usually maps to its own target group. Fourth, health checks. ALB constantly checks the health of your ECS tasks. If one becomes unhealthy, ALB automatically stops sending traffic to it and only routes requests to the healthy ones. This ensures high availability. Fifth, security groups. These act like firewalls for your load balancer. They control who can send requests in, and what outbound connections are allowed. Next, the DNS name. Every ALB is given a DNS name by AWS. This becomes the public entry point for your application, and clients connect through this address instead of talking directly to containers. And finally, load balancer nodes. Behind the scenes, your ALB isn't just one machine. It's actually made up of multiple nodes, spread across different availability zones in your VPC. These nodes are the actual servers that process client requests and forward them to your ECS tasks. Having multiple nodes ensures high availability. If one node goes down, others continue serving traffic. That's why, when you create an ALB, AWS asks you to select at least 2 availability zones, to make sure your load balancer is fault-tolerant and resilient. Together, these components make ALB both powerful and flexible for ECS workloads. When we connect ECS with an application load balancer, the integration depends on the launch type. First, EC2 launch type. Here, ECS tasks run on EC2 instances. The ALB sends traffic to the EC2 host, and the ECS service on that host ensures the traffic reaches the right container. Second, Fargate launch type. Fargate tasks get their own unique IP addresses. The ALB can route traffic directly to each task, there's no EC2 host involved. Let's recap the traffic flow when using an application load balancer with ECS. First, a client sends a request to the application load balancer's DNS name. Before anything else, security groups come into play. They act like firewalls, allowing only permitted traffic to reach the load balancer and protecting your applications from unwanted access. Next, the listener receives the request on port 80 for HTTP or port 443 for HTTPS. Then, listener rules are applied to determine which service or target group should handle the request. The ALB selects a target group, which contains all the ECS tasks registered for that service. It then ensures the request goes to a healthy target based on health checks, so traffic never reaches an unhealthy task. The request is forwarded to the ECS task, which processes it and generates a response. Finally, the response travels back through the ALB and reaches the client, completing the round trip. This flow ensures that your application is secure, highly available, and scalable, while clients get a seamless experience. Now that we understand the basics of ALB and ECS integration, let's dive deeper into ALB routing in ECS. Application load balancers are not just simple traffic distributors. They allow you to route traffic intelligently, based on rules you define, making your services more flexible and efficient. First, host-based routing. With host-based routing, you can direct traffic depending on the domain name the client requests. For example, api.example.com could be routed to your ECS service handling APIs, while app.example.com could go to your front-end service. This allows multiple applications to share a single ALB without conflicts. Second, path-based routing. Here, the ALB looks at the URL path of incoming requests. For instance, /API/users could go to your user service, while /API/orders goes to the orders service. This makes it easy to manage multiple services under the same domain efficiently. Third, routing to specific ECS target groups. Each ECS service is associated with a target group. ALB routing rules ensure that traffic is sent to the correct target group, even as your tasks scale up or down dynamically. This keeps traffic flowing to the right containers at all times. Fourth, dynamic scaling. As your ECS tasks scale up or down, the ALB automatically registers new tasks and deregisters old ones from the target groups. This makes sure that your application can handle changes in traffic smoothly. Fifth, task health. ALB continuously performs health checks on all tasks. Requests are only sent to healthy tasks, so even if a task fails or is being replaced, your users won't notice any downtime. This ensures high availability and reliability for your application. In short, ALB routing in ECS gives you flexibility, reliability, and scalability, letting you run multiple services efficiently under one load balancer while keeping traffic flowing smoothly. Now that we've covered the basics of ALB and routing in ECS, let's explore some advanced features that make the application load balancer even more powerful for production workloads. With SSL or TLS termination, the ALB handles all the encryption and decryption of HTTPS traffic. This means your ECS tasks don't have to do the heavy lifting of encrypting or decrypting requests, which improves performance. It also simplifies certificate management, because you only need to manage SSL certificates at the ALB level instead of inside each container. ALB fully supports WebSockets, allowing real-time, bidirectional communication between clients and your ECS tasks. This is essential for applications like chat systems, live dashboards, or collaborative tools where instant updates are required. Sticky sessions, also called session affinity, allow the ALB to route all requests from a specific client to the same ECS task. This is helpful for applications that store session data locally in the container, ensuring a consistent user experience. ALB provides detailed access logs and CloudWatch metrics, which let you monitor traffic patterns, analyze usage trends, and troubleshoot issues quickly. You can track which requests were served, how long they took, and which ECS tasks handled them, giving you full visibility into your application. Next, redirects and fixed responses. You can configure the ALB to handle HTTP to HTTPS redirects automatically, or even return fixed responses for certain requests, like maintenance messages or custom error pages. This gives you flexibility in handling client requests and improving security. Advanced routing lets you direct traffic based on host headers or URL paths. This allows you to run multiple services behind a single ALB efficiently. With cross-zone load balancing, the ALB can distribute traffic evenly across multiple availability zones. This improves fault tolerance and ensures high availability, because even if one availability zone goes down, traffic continues flowing to healthy tasks in other zones. All of these features together make the ALB a robust, flexible, and highly reliable solution for managing traffic to your ECS applications, whether you're running a few tasks or hundreds. Alright, that's it for the ECS load balancing basics. From the next video onwards, we'll begin the hands-on sessions for load balancing in ECS, and go through everything step by step. Thanks for watching. If you found this video helpful, please leave a comment and share your thoughts below. I'll see you in the next video.